In section 10.3, we're going to explore different gas laws, starting with Boyle's law, which you should be familiar with from last year. The volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. So what this tells us is that if you increase the volume, then the pressure will go down. Or if you decrease the volume, the pressure will go up. That's an inverse relationship. In this particular example, or this picture, we have a volume of gas, which is equal to 60 milliliters, that's trapped under mercury at atmospheric pressure. Now, if we add some mercury to the open end of the tube, that additional mercury is going to add more pressure to the gas. And because the pressure is increasing, the volume will decrease, and that 60 milliliters of gas will then be compressed into 30 milliliters of gas. So gases can be compressed. If you are to plot the relationship of volume versus pressure, this results in a curve, which indicates that it is an inverse relationship. This curve indicates that volume versus pressure is an inverse relationship. So we get this line here. If we were to say that pressure times volume is a constant, this would mean that a plot of the volume versus 1 over the pressure, or the inverse pressure, will be a straight line. Also, before I move on to Charles' law, keep in mind that Boyle's law, the relationship is P1 times V1 equals P2 times V2. So Charles talks about volume and temperature. He said that the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature. So here we can see a nice linear relationship that's showing us that as the temperature goes up, the volume is also going up. Another way of thinking about this is that if you heat a gas, it's going to expand. Or if you cool a gas, it will contract. When you heat something, it expands. You cool something, it contracts. This is a direct relationship, and this is Charles' law. Therefore, his relationship says that volume divided by temperature is constant. So the slope of this line is constant. If we did the change in y over the change in x, or volume divided by temperature, that slope would be constant along that line. We can derive from that the relationship V1 over T1 equals V2 over T2. Keep in mind that when you're doing gas laws involving temperature, you must always use Kelvin. Okay, Avogadro's law, the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. Another way of saying Avogadro's law is that 1 mole of any gas will occupy 22.4 liters at standard temperature and pressure. Sample exercise 10.3, evaluating the effects of changes in pressure, volume, moles, and temperature on a gas. So suppose we have a gas confined to a cylinder as shown in figure 10.12 in your book. So this is just a cylinder with a piston. And if we think about the following changes occurring, if we heat the gas that's in the piston from 298 Kelvin to 360 Kelvin, while maintaining the piston in the position shown in the drawing. So we're keeping the volume constant. We're not allowing the piston to move up or down, but we are changing the temperature. We're increasing the temperature. So increasing the temperature would make the molecules move faster. There would be more collisions. And we can go down to the solution. It says 4A, heating the gas while maintaining the position of the piston will cause no change in the number of molecules per unit volume. So our density per se would stay the same. The distance between the molecules and the total moles of gas remain the same. They're constant. But the increase in temperature will cause the pressure to increase. This is Charles' law, relating pressure and temperature. And again, you can think about it as the molecules increasing their speed as they're being heated, their kinetic energy is increasing, and there's more collisions, hence higher pressure. In B, it says that we're going to move the piston to reduce the volume of a gas from 1 liter to 0.5 liters. So in this case, we're reducing the volume of the gas. We're compressing it. Compress, that has to do with pressure, right? So changing the volume of a gas to a smaller area is definitely going to increase the pressure. So if we look at the solution, it says moving the piston compresses the same quantity of gas into a smaller volume. We haven't added any gas or taken any away, so the total number of gas molecules of gas and the total number of moles remains constant. The average distance between the molecules, however, is going to decrease because of the smaller volume. So the molecules are going to get closer together in that confined space, and the reduction in volume causes the pressure to increase. This is Boyle's law. So again, pressure and volume have an inverse relationship. As the volume decreases inside of the piston, the pressure is going to go up. C, inject additional gas through a gas inlet valve. If we add more gas, we're going to have more molecules and therefore more collisions. So injecting more gas into the cylinder while keeping the volume and temperature the same will result in more molecules and therefore a greater number of moles of gas, or greater particle density if you want to think about it that way. The average distance between the atoms must decrease because there's more of them, so the pressure would then increase. You're going to have more collisions, and this would be Avogadro's law. For practice, I want you to think about these scenarios. What happens to the density of a gas as A, the gas is heated in a constant volume container, B, the gas is compressed at constant temperature, and C, additional gas is added to a constant volume container.